Alright, so this video is going to be more on curve sketching. So none of this, that's an R, that's a V. None of this material is new. This is just more practice of the things that we've been doing and kind of tying all sorts of things together and maybe looking at some different functions than we looked at when we did the curve sketching the first time. So there are a few things to think about. One thing to think about, one of those things is the domain of the function. The other thing is whether or not there's symmetry in the function. So if you think about the domain, that might help you consider a part of the graph that you might otherwise have skipped and just not drawn. Symmetry can help you figure out how to draw the graph, because if you think that there's some sort of symmetry there and you have enough information to graph one part of one curve, then maybe you can use that symmetry to draw the other side. There are other things that we always want to do the math to check, and one of those is the intercepts. You always want to check for the y, goodness gracious. You always want to check for the y-intercept. And the reason you want to check for the y-intercept is because you just have to plug 0 into x, and this is usually fairly easy to find. You also want to find the x if it's easy to solve. If it's terribly difficult to solve or it's not possible with the math that we know to solve, then don't sweat it. But if you can, you'd like to find that, because any point that we put on the graph is going to make it easier for us to draw the graph more accurately. The next thing you're going to look for is asymptotes. So we've got 3 to check. You want to make sure to know whether or not there's a horizontal, a vertical, or if there's not a horizontal, you want to check to see if there's a slant asymptote. You want to look to know where the increasing and decreasing intervals of the graph are and where the extrema is. And those you're going to find, like we did earlier in the unit, from the first derivative. You also want to check the concavity of the graph and the points of inflection. And just like before, we're going to get those from the second derivative. So we're just going to tie everything that we've done all together. Some of these problems are a little bit messy to find the answers to, and really it just comes down to being very, very careful with your algebra and making sure that you are mathematically doing things accurately. So we just have to be really careful. So for the example, we are going to sketch the graph. And the first function that we are going to look at is y equals 2x squared divided by x squared minus 1. And there's not necessarily a specific order you have to go through when you look for these things. I went ahead and I just am doing my example problem kind of in this order, because that kind of helps me to do it like a checklist. So the x-intercept for a rational function is whatever would make the top equal 0, because that's where the y value of the problem would be 0. And the top of this equals 0 when x equals 0. So my x-intercept is the point 0, 0. My y-intercept is what I get when I plug 0 in for x. So if I plug 0 in for x, I get 0 on the top and divided by -1 on the bottom. So my y-intercept is also 0, 0, which makes sense. If you get those as an answer, they should match up. Vertical asymptotes come from making the denominator equal 0. So x squared minus 1 equals 0. I can factor that. X plus 1, x minus 1 equals 0. So my vertical asymptotes are at x equals -1 and x equals +1. For the horizontal asymptote, I'm going to look at the limit as x approaches infinity of 2x squared divided by x squared minus 1. And so when I plug infinity in, infinity squared and infinity squared down there, those two are going to cancel with each other, and I just get 2. And if I was to find the limit as x approaches -infinity for the same function, Since those numbers were being squared, it doesn't make any difference. It's still just 2. Slant asymptote, there wouldn't be any since there was a horizontal asymptote. So now I've found all those things. I'm going to go ahead and look at the things that I can find from my first derivative. So for this, I have to do the quotient rule. You could also do the product rule. You could say x squared minus 2 to the negative 1 power if you want. So I'm going to go ahead and do the quotient rule. I've got low d high minus high d low divided by low squared. And then I need to go ahead and clean this up a bit. So 4x multiplied by x squared is 4x to the third. 4x multiplied by negative 1 is negative 4x. And then I have negative, and 2 times 2 is 4, x to the third. So those cancel. I have negative 4x on the top and x squared minus 1 squared on the bottom. So if I want to know where my critical numbers are, I can take the top and make it equal 0. So negative 4x equals 0, and that gives me x equals 0. And then down here on the bottom, x squared minus 1 squared, we have already factored that, and the fact that it's squared just means that the difference of squares that I can see there is just happening twice. I don't get any more answers there, I just am being a little bit redundant. So when I make my sign chart, I'm going to be checking here at 0, at negative 1, and at positive 1. And so the most cleaned up version of my derivative was this part right here. And so at this point, whenever you have a derivative that is difficult to plug a number into in your head, just plug the number into the derivative. So I went ahead and plugged in negative 2, and I got that the answer was positive. I plugged in negative half, and I got that the answer was positive. And again, I'm evaluating the derivative here because the sign chart only works if you plug it into the derivative. I plugged in positive half, and I got a negative answer. And then I plugged in positive 2, and I also got a negative answer. So that tells me that my graph is increasing from negative infinity to negative 1 and negative 1 to 0. And it tells me that I'm decreasing from 0 to 1 and 1 to infinity. And then if I look here, this is the only place where a sign change happens, and it goes from increasing to decreasing, and so that's a maximum. And my maximum is where x equals 0. And we already know from the other information that we've found that the point 0, 0 is on the graph. And so my maximum must be that x-intercept slash y-intercept, so that same point. Means a lot for our problem. Okay, so there's all the things we could find from that. Next, we need to do our second derivative. And at this point, when I was writing the notes out, I did do the quotient rule in the second derivative, and it was a hot mess, and I did not enjoy it. So it's a little bit easier for the second derivative to bring this denominator up to the front, or up to the top, I mean, and call it an exponent of negative 2, and then just do the product rule instead. So I'm going to go ahead and get a new sheet. So I have... Actually, I might actually do a new sheet so I can show both papers at once. All right, so I'm just going to rewrite my first derivative as negative 4x times x squared minus 1 to the negative second power. And now I need to go ahead and do the product rule to find my second derivative so that I can finish this problem that is taking forever. All right, so the first one multiplied by the derivative of the second one, and the derivative of this requires the use of the chain rule. So I dropped the exponent to the front, subtracted 1 from the exponent, and now I'm multiplying by the derivative of the inside. So that was me doing the first half of the product rule, the first piece multiplied by the derivative of the second piece, plus the second piece multiplied by the derivative of the first. And now I'm going to go ahead and just clean it up a little bit. So this negative 4x, this negative 2, and that 2x all have positive exponents with them, so they belong on the top of that fraction. So negative 4x times negative 2 is positive 8x. Positive 8x times 2x is 16x squared. And then this part right here gets to go on the bottom of the fraction because of that negative exponent. Plus, and then same thing over here, negative 4 goes on the top because it has a positive exponent, positive 1, and then this goes on the bottom. Now, if you recall, we need to find our critical numbers to be able to find the concavity and the point of inflection, and we can't solve for critical numbers by taking the top of the fraction and setting it equal to 0 and the bottom of the fraction and setting it equal to 0 while our answer currently has two fractions. We need to write those two fractions together as one fraction. So that means we need a common denominator. So this denominator has x squared minus 1 being multiplied 3 times. This side only has twice. So that means that to get my common denominator, I just need to multiply by x squared minus 1. And I know that this is kind of an obnoxious process, but I promise you this is easier than what I went through when I tried to do the quotient rule. I'm not kidding you, I gave up. I don't know if I did something wrong, but I didn't feel like going back and checking it. So at this point, both of our denominators are the same, x squared minus 1 to the third. This one is still 16x squared, so that one's good. And then over here I can take this negative 4 and go ahead and distribute it. So that gives me negative 4x squared plus 4. So my second derivative is 8x squared, not 8x squared, I lied, 12x squared plus 4 divided by x squared minus 1 to the third. So if you look at the top, that is not factorable. You can't solve that because if you tried to set the top equal to 0, 12x squared plus 4 equals 0, you would end up subtracting the 4 over, so you'd get 12x squared equals negative 4, and you would divide by 12, and you'd still have a negative number, and then you would be square rooting a negative number. So there are no critical values that come from making the top of the fraction equal 0. So the second derivative cannot equal 0. It's not possible. But we can look at where the second derivative is undefined, and that's where the bottom equals 0. So now, if we look at this, and we want to say x squared minus 1 to the third equals 0, if we were to factor this, it would just be x plus 1x minus 1, and then x plus 1x minus 1, and then x plus 1x minus 1. It's just those same factors for difference of squares, but 3 times. So I'm going to say this is just x equals 1, x equals negative 1. And then I can go ahead and do my sign chart. And again, when I did this problem, this was hard for me to kind of plug numbers in my head, so I went ahead and I just plugged numbers in using my calculator. So negative 2, if you plug in negative 2, you find that this value over here is positive. If you plug in 0, you'll find that the answer is negative, and if you plug in positive 2, you find that it's positive. So my conclusion, based off that, is that the graph is concave up from negative infinity to negative 1, and from 1 to positive infinity, and it is concave down from negative 1 to positive 1. And then our other conclusion would be that we have points of inflection at x equals negative 1 and x equals positive 1. So you would have started writing points, which is what I did when I wrote my notes, and then I went back and I looked at my other sheet and I was like, well, I can't plug those in because those are vertical asymptotes. Those are the values that make the denominator show that the whole function is undefined at those values. So I went back and I said, all right, for points of inflection, there are none, because the parts of our graph that change it from concave up to concave down are not points, they're actually asymptotes. All right, and then at this point, you are ready to sketch your graph. Thank goodness. Alright, so I like to be tricky and use these little graphs that are sticky notes. So, if I look at all the things I found, I know I have an x-intercept and a y-intercept at 0, 0, so I can draw that. I know I have vertical asymptotes at -1 and +1. I know I have a horizontal asymptote at 2. I know that the maximum of the graph is at 0, and I know that the whole graph is concave down from -1 to 1. So based off what I know about concavity, based off what I know about asymptotes, I know that this, it looked like I ran into the asymptote, but I did not mean to. So I know that this curve should be a U shape going down, and that the curve is approaching those asymptotes. I know that the rest of the graph is increasing on either side of this, so it's concave up on these two sides. And I know that, let me look at it, my graph is increasing from -∞ to -1. So if I consider what I know about the concavity and what I know about how it has to increase, that means that if the curves have to be either down here or up here, then it only makes sense for the curve to be up here. And that's because it's concave up, but also because this graph has to be increasing. Now, I know that my points in here may not be accurate, but I do know that this is the overall shape of the graph because we know that curves approach asymptotes. That's how they work. Now we're decreasing from 1 to infinity, and we are concave up from 1 to infinity, and so that tells me that the other curve should end right here. And then I can kind of double check the other stuff. So I did see that my graph is increasing from -1 to 0 and decreasing from 0 to 1. And so this fits all the information we found. And if you go ahead and graph it on your graphing calculator, you're going to find, I'm a really bad multitasker. You're going to find that the graph that we sketched is actually correct. So 2x squared divided by x squared minus 1. And if I am so zoomed in right now. Oh, that's perfect. Kind of works. Well, I might be too zoomed in to see everything. So there's my graph, and it matches. Woohoo!